Good morning. I welcome you all for this lecture on basic thermodynamics in the module 2 of fluid dynamics and turbomachines. In the last 4 weeks, you have studied basically different aspects of fluid dynamics. From now on, we will talk about turbomachines, its types and different features. As we have been told that fluid dynamics forms an essential background information that is required for understanding and appreciating the performance of turbomachines. Another fundamental subject which you require to better appreciate turbomachine is thermodynamics. So, today we will start with some basic thermodynamics, a recapitulation of what you have studied in your course. If you are not comfortable with thermodynamics, you may look at some textbooks on thermodynamics, and you can also refer to Professor S.K. Shom from IIT Kharagpur's excellent lectures on thermodynamics available in NPTEL. Because in this course I will talk about only those aspects of thermodynamics which I require for explaining turbomachines. So, we will start with first law of thermodynamics. First law of thermodynamics is essentially the conservation of energy. When we talk about first law, we talk about the interaction of heat and work and the changes in different forms of energy. Let us say we have a system and some heat is added to the system and some work is done by the system. So, first law tells me that there is a property called energy of the system which will change as a result of the interaction of heat and work with the system, and we get the first law of thermodynamics, del Q minus del W equal to dE. Q, as you have understood, is the heat transfer and W is the work done. There is a sign convention. It is not necessary that you have to follow this sign convention, but this is mostly followed by all textbooks, and I will also follow it here, that heat transfer is considered to be positive when heat is added to the system. Similarly, we can talk about work done. Work done is considered to be positive when work is done by a system. Also, another thing you may be wondering, that why we have del Q to talk about an incremental addition of heat and del W for an incremental work done, whereas we have dE to show the corresponding change in energy. This is because, as you know, that property like energy is a point function, whereas the heat transfer and the work are path functions. So, to make the distinction, we are going to use del Q and del W, whereas for a property like energy we will talk about in dE. This energy E comprises of internal energy, which is given by capital U, the kinetic energy which is a macroscopic property which is given by half mv square, and also potential energy which is given as mgz, where z is the elevation from some datum. We may also express this energy in terms of specific energy E, which comprises of then the specific internal energy small u, half v square and gj respectively. Next thing we have to talk about is the control volume approach. See, in case of turbomachine, the fluid flow enters a turbomachine and then leaves. In the process there can be heat and work transfers. We have to understand that this is a flowing process. This is not a non-flow system like you can see in some other examples, and this is solved using a control volume approach. Also, another point I need to mention here is, I am not considering the internal details of turbomachines. I am considering turbomachine essentially as a black box. I just want to know what crosses the surface given by this dashed line, which is the control surface, and what is the net change. So, with this description, we can say that the mass flow in any control volume can be m dot in and m dot out. We can have the energy transfers, which is we have given by our convention, the work is done by the machine, which is W prime. Please note that we are talking about W prime, which is the rate of work done, and we have taken it as positive, but turbomachines need not always produce positive work. I will come to that shortly. Similarly, we can talk about the heat transfer rate at Q prime from the surrounding to the control volume, again following the sign convention that we have adopted. In case of turbo machines, there is a steady state steady flow, which means there is no accumulation of mass inside the control volume. So, whatever mass comes in also leaves, and we will follow this steady state steady flow energy analysis. So, let us look at turbo machines. So, we have m dot in and m dot out. Very soon we will show that m dot in equal to m dot out, but for the time being let us keep m dot in and m dot out as notations different, and in and out shows the areas. So, conservation of mass yields m dot in minus m dot out is dmCV dt. In order to understand it better, let us think about a tank. We have a tank in which we fill water. So, what happens? There is a pipe, or there may be multiple pipes which bring water into the tank, and there is an outlet, or there could be multiple outlets through which water leaves the tank. Now, let us take a simple case when there is only one inlet and one outlet. So, if water enters the tank with some flow rate m dot in and leaves with a flow rate m dot out such that m dot out is less than m dot in, then what do you expect? You will find that the level of water in the tank increases. That means more and more mass of water gets accumulated in the tank. This change of mass in the control volume in the tank in our case is given as dmCV dt. Another thing we need to understand, background information to appreciate this steady state steady flow energy equation. With the flow process, we have something what is so called the flow work or the pressure energy. Let us say I have a control volume given by this dashed line, and this blue on the left bottom shows the pipe which brings the fluid in, and the top right shows the fluid that leaves the control volume. And we can say that the pressure, the area of the interface and the velocity are given as P1 A1 V1 at the inlet and P2 A2 V2 at the outlet. So, we can say that if we have a fluid element which gets displaced by a distance delta x, and then the force that is required to be pushed to push against the pressure P1 is given as P1 A1. I am talking only about the inlet. The corresponding analysis can be done for the outlet. So, the work done to push the fluid element by a distance delta x or dx as I have used is nothing but f dx, which is P1 A1 dx. So, the flow work per unit mass is going to be given by P1 A1 dx divided by rho 1 A1 dx. So, you will get that work done, flow work per unit mass flowing in is equal to P1 by rho 1, which means we can also write in terms of specific volume as P1 V1, where V1, the small v1 is specific volume, the capital V, please note, is not volume, it is the velocity. Okay? And similarly, you can talk in terms for the flow work going out as P2 V2. To get a better appreciation of flow work, we can say that we can take an example. Let us say that you are standing in a queue trying to enter a cricket stadium to watch a match. So, what happens? You are trying to push your neighbor so that you can go fast, and that means you are doing some work on your neighbor, and the neighbor is in turn pushing his neighbor. So, now if we think about our fluid element waiting in queue to enter the control volume, it is actually pushing the neighboring fluid element, it is doing work on the neighboring element against the pressure of P1. So, we can think about flow work either in terms of the flow or the work done, or in terms of the energy that is being stored on the neighboring element. Both ways you can talk about it, and hence sometimes it is called the flow work, sometimes it is called the pressure energy. So, we will talk about conservation of energy. So, we already have learnt the first law of thermodynamics, which says that del Q minus del W equal to dE. Essentially, this is the same thing we are going to use, but in a slightly different form. So, we can say that Q prime, which is the rate of heat transfer, plus m dot in E in minus m dot out E out minus W prime minus W prime flow in plus W prime flow out is equal to dECV dt. I will talk about E in and E out now. See, E in is the specific energy which comprises of the terms like internal energy U, which is due to the molecular motions, plus the macroscopic kinetic energy like half V square, plus the potential energy Gz. So, if we put this in along with the expressions for flow work we have done so far and we rearrange it, we can get that Q prime plus m dot in U in plus half V in square plus Gz in minus m dot out U out plus half V out square plus Gz out minus W prime minus m dot in P in V in, that is a flow work for the inflow, plus m dot out P out V out is equal to the net change in the energy in the control volume dECV dt. We can now arrange all the terms that are with m dot in, like the terms in this bracket with the term P in V in, and similarly for the terms m dot out in this bracketed terms with the flow work term, and put it in this fashion. We can get that Q prime minus W prime plus m dot in, within bracket we get U in plus P in V in plus half V in square plus Gz in minus the corresponding terms for the flowing out m dot out U out plus P out V out plus half V out square plus Gz out equal to dECV dt. Let us look at this term U in plus P in V in. This is nothing but the enthalpy you have talked about H in. Similarly, we can talk about U out plus P out V out is nothing but H out, H being the static enthalpy. So, now if I rewrite it in terms of the enthalpies in place of the internal energy and the flow work, we get the final form which we need is Q prime minus W prime plus m dot in H in plus half V in square plus Gz in minus m dot out H out plus half V out square plus Gz out is equal to dECV dt. But I have already told you that in turbo machine we talk about steady state steady flow, which means there is no accumulation of mass, there is no accumulation of energy, and hence we can say that dmCV dt is equal to dECV dt is equal to 0, and we get steady state steady flow condition, which means we can simplify the expressions that we have got. We will say that m dot in equal to m dot out equal to m dot, and the energy equation reduces to Q prime minus W prime is m dot H out minus H in plus half V out square minus V in square plus G Z out minus Z in. All right. Let us look at the terms again. H is a specific enthalpy, V square is the kinetic energy per unit mass, and Gz is the potential energy again per unit mass. Except for hydraulic machines, which we will talk little later, the last term, that is the change in the potential energy, is insignificant compared to the other changes. In such cases, we can drop the last term. That means for any turbo machine handling air or steam or any other gas, the change in potential energy can often be neglected, and we get that Q prime minus W prime is m dot H out minus H in plus half V out square minus V in square, and this gives me equal to m dot H 0 out minus H 0 in. I am introducing a new term here which is H 0 out, and you can easily understand H 0 is nothing but H plus half V square, which means H 0 out is nothing but H out plus half V out square, H 0 in is nothing but H in plus half V in square. This H 0 is called the stagnation enthalpy, So, let us take an example of the steady flow energy equation, the flow in a nozzle or a diffuser. So, this is a nozzle in a conventional sense we have drawn, this is a schematic. So, 1 is the inlet, 2 is the outlet, and the flow direction is from the inlet to the outlet. This line hatch lines is my attempt to show that the flow is adiabatic, and in that we say that the nozzle is insulated, which means that Q prime equal to 0. The nozzle does no work because it is a stationary component, and hence we can say that W prime equal to 0, and hence the first law of thermodynamics reduces to, in the absence of potential energy change, as m dot H02 minus H01 equal to 0, or H02 is equal to H01. I have shown it for nozzle, but the same can be talked about for diffuser as well. And if we say that the approach velocity V1 is small, as is often the case, then we can write the changes in the static enthalpy and the velocity of the kinetic energy changes, and we can get that V2 is root 2 H2 minus H1. When we will discuss turbomachines, particularly we will talk about steam or gas turbines, we will talk about the role of nozzle and diffusers in much more detail at that time. And that time you should recollect that we have talked about the change of static enthalpy giving rise to a velocity increase. The next example that we can talk about is steady flow energy equation as applicable for flow in a turbine. Here again we are talking about the turbine is insulated, which means that Q prime equal to 0. Please note that the heat transfer in turbines may be present, but it is not significant. So, I am taking it to be 0, and in most of the applications this is a fair assumption. If in any particular case you come across there is a significant heat transfer from the turbine or from the compressor to the surrounding, you have to account for it. So, we assume that the turbine is insulated here and Q prime is 0, the flow is from the 1 to 2, and there is a work transfer. This is a big difference. So, work is done by the turbine, a positive power, and we say that W prime is greater than 0. So, similarly neglecting changes in the potential energy as we have done in the case of flow nozzles or the diffuser, we can say that minus W prime equal to m dot H02 minus H01, or we can say that Wt prime, which is the work done, rate of work done or the power produced by the turbine, T for turbine, is equal to W prime m dot H01 minus H02. Let us pause here for a minute. We say that the work done by the turbine is positive because it is a positive power, and we look at it and we find that H01 must be greater than H02 in order to Wt prime or W prime to be greater than 0. So, what happens? It shows that there is a fluid which is coming into the turbine, and it gives a part of its energy which makes the blades to move, and we get electricity as an output. So, there is a transfer of energy from the fluid to the machine, and hence we get that the fluid that is coming out of the turbine is having less energy. Of course, if the kinetic energy changes are negligible, as is often the case, then we can say that Wt prime is m dot H1 minus H2. That is, instead of using stagnation enthalpy difference, we will talk about the static enthalpy change. If we take a compressor, the main difference between the turbine and the compressor is in the fact that in case of a compressor, the work is done on the system. So, there is a negative power. Let us take a simple example. You might not have seen a compressor, but we can talk about the household electric fan. The fan produces the air which we are all feeling comfortable about. But how does it work? It does not work on its own. You have to turn on the electricity. So, electrical energy gets converted into mechanical energy, and then we are talking about the blades move and it produces the air motion. So, now we are talking about a compressor which is a similar instrument, similar equipment, which talks about a negative power, that is W prime is less than 0. Following the same analysis as we have done for turbine, and that is neglecting changes in potential energy, we can say that Wc prime is equal to minus W prime equal to m dot H02 minus H01. So, let us again look at it. In thermodynamics, you might have come across that we talk about the work done by the compressor as minus, let us say 5 kilowatt. But in reality, when we want to buy a machine, and let us say we are trying to buy a pump, we do not want to buy a motor which is minus 5 kilowatt. We want to buy a motor which will run the pump which is having a capacity, let us say 5 kilowatt. So, to get it positive, we are now talking about WC prime as minus of W prime, which makes it positive, and we get m dot H02 minus H01. What it means? That the fluid leaving the compressor, fluid leaving this turbo machine actually has more energy, because the energy is being added by the blades. And if the kinetic energy changes are negligible, then again we can talk about m dot H2 minus H1. So, let us summarize the steady flow energy equation, whatever we have learned so far. For most turbo machinery applications, the flow processes are adiabatic, that is, there is no heat transfer, and it is permissible to write Q prime equal to 0. And we can write that minus W prime equal to m dot H0 out minus H0 in, and in case of turbines producing work, we can write that Wt prime equal to W prime, which is m dot H0 in minus H0 out. And in case of compressors, W prime is less than 0, which is a work absorbing machine, and we can say Wc prime is m dot H0 out minus H0 in. Now we come to the second law. Second law of thermodynamics is a very fundamental law, because it gives an additional qualification on the energy transfers. So, while first law talks about the conservation of energy, and second law will add a restriction. First law does not tell you whether 100% of the work can be converted into heat or vice versa. Second law puts a restriction on the direction of flow of heat and work. For example, we know from our common experience that water falls from a higher level to a lower level spontaneously. Heat flows from a higher temperature to a lower temperature naturally. So, then it never happens in the other way. First law does not really say that such a process is not possible. The second law brings in the directional aspect. You can actually take water from the ground floor to a multi-storied building, top of the multi-storied building, by using a pump. So, that means you have to put in an external agency to supply the work. So, these concepts, these directional constraints are added by the second law. Second law also gives rise to a property called entropy, and it is defined as ds is equal to del q reversible. We are talking about a reversible process by T. Next important thing we need is the Clausius inequality. For steady one dimensional flow through a control volume in which the fluid experiences a change of state from in at entry to out at exit, we can write that del q prime by T into out is less than equal to m dot S out minus S in. If the process is adiabatic, that is, there is no heat transfer, then what happens is S out is going to be greater than equal to S in. This inequality that comes for an irreversible process. For a reversible process, that is, if we talk about a reversible adiabatic or isentropic process, then we get S out equal to S in. We will see how these processes take place and depict it on a HS or a TS plot very soon. So, now combining the information that we have gathered from first and second law of thermodynamics and using isentropic conditions and neglecting motion, gravity, etc., that is kinetic energy, we can say that del q reversible is TdS, that is, we get from the second law, and from the first law we get that del q equal to du plus pdv. This is for a non-flow system, and where only pdv work or the displacement work is the only form of work which is possible. And then combining these two, we can write TdS equal to du plus pdv. But please note that though we have got the TdS equal to du plus pdv as a condition, as a relationship under different assumptions, but this relationship is valid for all processes. Why? Because all the this is actually a relationship connecting different properties, and properties are point functions. So, it does not depend on what process, what path the change has taken place. So, this is valid for all processes. And now, if we bring in enthalpy, which is H equal to U plus PV, and talk about the changes in enthalpy dH as du plus vdp plus pdv, and then substitute it back, we get that Tds equal to dH minus vdp. We will make use of this relationship in the next slide. So, summing up the key relationships shown earlier, we can say that from the first law we get q prime minus w prime equal to m dot h out minus h in plus half v out square minus v in square plus g z out minus z in, which for an incremental change we can write that del q prime minus del w prime equal to m dot dH, that is the incremental change in enthalpy, plus half d v square. Here again I am talking about the change in the v square quantity. D v square is a notation I am using to talk about the change in the kinetic energy per unit mass, plus g dz. And this when combined with second law we get the del q prime is less than equal to m dot T ds or m dot dH minus v dp or dp by rho as I have written here. So, now let us club the first and the last relationship in the next slide. So, we get that del w prime is less than equal to minus m dot dp by rho plus half d of v square plus g dz. For a turbine, w prime is greater than 0, and this brings us to a very important conclusion that the work that can be obtained from a turbine, the power that can be produced by a turbine has a maximum which is achievable only under an ideal condition of isentropic. So, we get that Wt prime is less than m dot out to in dp by rho plus half v in square minus v out square plus gz g of z in minus z out. You please note and take care of this inequality sign. That means under no circumstance the turbine can actually have any power output greater than this value. That violates the second law of thermodynamics. In fact, for all real applications this equal to sign also is not valid, and we will have the upper limit only as an ideal case for an isentropic flow. For a compressor, however, W prime is less than 0. So, if we swap the directions of this inequality, we just bring it to the other side and rewrite it, then we can say that W C prime, because I have now made it into the positive way of expressing the power as we have done, is m dot in to out integration dp by rho plus half v out square minus v in square plus g z out minus z in. So, here you see that this dp by rho is actually for both turbine and compressor is actually indicative of the fact that we need to rely on what is the thermodynamic process. Is it reversible or irreversible? If it is irreversible, because of many reasons we will come across in thermodynamics textbooks, I will talk about the losses that take place in the turbomachines later on, we will get that this inequality sign comes in. That means, in order to get a definite work output from a compressor, the work that you have to add to the compressor, the power that you have to supply to the compressor should be greater than certain minimum quantity. This is just the converse of what we see in turbine. In turbine, I repeat, we get a work output from the turbine, the power produced by the turbine less than a maximum achievable quantity. And so, these two conclusions are written here, that real flow means the work output from turbine will be less than that of the ideal one. This real flow means the fluid has viscosity, there are mechanical friction losses, and hence the output will be less. And for pumps and compressors, actual work input will be more than the ideal one. These are because of the losses, and hence we can say only a part of the energy that is added in case of pump or extracted in case of turbine appear as useful energy. This term useful energy is very important in the turbomachine literature. We will talk about it now. So, let us look at the schematic. This is my idea of putting in a cartoon form what happens in a pump or compressor. The total energy that is transferred from the impeller, that is the rotating blades, to the flow, only a part of it, maybe a major part of it, but only a part of it is given to the transfer to the fluid in a useful fashion, and there is an energy rise across the turbo machine in the fluid, whereas the loss accounts for the remaining portion. In case of turbine, the total energy available with the fluid we cannot extract. That energy that goes into the blades in the form of torque and the power produced is only a fraction, maybe a large fraction, maybe 80, 90, 95%, but not 100%. There is a component called loss. So, engineer working in turbo machine companies, what you would like to do is try to minimize the loss. So, in this lecture series, whatever we are going to talk about, we will try to understand how this turbo machine performs, what are the causes of these different losses, and how we can improve it. And now we come to a very important definition of specific work. The difference between the useful specific energy content of the flow between the two ends of the turbo machine is defined as the specific work done between the inlet and the outlet. Please note all the terms which are marked in different colors. The difference, when we are talking about turbo machine, there is one inlet, one outlet, and we are talking about the difference in the energy that is available with the fluid. You are making the measurement, let us say you are doing an experiment, you find out by some means, we will talk about it later when we talk about the experimental procedures. We find out the energy content of the flow that comes into the turbo machine and the energy content of the flow that leaves the turbo machine. Now find out the difference between the useful energy and divide it by the mass flow rate, we get the useful specific energy. This is known as specific work in case of turbo machine, and this is one of the desirable features of the when you talk about the performance of a turbo machine. And to remind you that since it is a specific energy, there is energy per unit mass flow rate. So, it is joules per kg or meter square per second square. So, for hydraulic turbine, density is constant and the first law gets reduced to the combination gets reduced to the W T prime max. We are now using the equal to sign. So, we can write max is m dot into P in minus P out by rho plus half V in square minus V out square plus G Z in minus Z out. And specific work W is nothing but the work produced, maximum work produced, because that is the useful work we are talking about, the energy available across the turbo machine by in the fluid by per unit mass flow rate is given as P in minus P out by rho plus V in square minus V out square by 2 plus G Z in minus Z out, which is equal to many times given in form of G multiplied by capital H. This capital H is nothing but the net head utilized by a turbine. So, when we design a turbine, we have to know what is the head that is expected across the turbine. So, this is the net head H. Similarly, for a pump, rho is constant and we can get the specific work to be again established in terms of G into H, but in this case the relationship is P out minus P in by rho plus V out square minus V in square whole divided by 2 plus G Z out minus Z in. In this case, please note that this H is the head developed by the pump. So, we will come across these terms, the head, net head utilized by the turbine and the head developed by the pump when we talk about pumps and turbines in the next week. Now, I will quickly talk about the representation of these processes for a gas or steam handling machines on a HS plot or a TS plot. So, here we see the direction shows that it has come from 2 to 1. So, what type of process is it? Is it compression or expansion? Is it a compressor or a turbine? Of course, this is an expansion in a turbine. We are talking about the turbine, the inlet is at 2 and outlet is at 1, and we see that there is an expansion, there is a reduction in pressure, there is a reduction in enthalpy from 2 to 1, which is the actual process. Whereas, in ideal case, in isentropic process, if you see that there is no change in entropy, we see that from 2 it would have come to 1 S. This letter S here denotes the S is constant isentropic process. We can also talk in terms of the stagnation properties, which is nothing but H02 for example is nothing but H2 plus V2 square by 2, and or H01s is nothing but H1s plus V1s square by 2. So, you see one thing very clearly, that if I am talking about an idealized condition, isentropic condition, then the total enthalpy drop that I can talk about is H02 minus H01s. Whereas in real life, we, because of this irreversibilities, because of the losses, what we get it is H02 minus H01. That means the actual amount of power produced is related with H02 minus H01. If we want to talk in terms of static enthalpies, we can talk about H2 minus H1 or H2 minus H1s as the corresponding cases, and that will give rise to efficiency, as I will show you. So, this is with a gas or steam, and specific work in this case, as we obtain from the HS plot in case of steam turbine, we can say that W with the specific work is W prime by m dot is nothing but H02 minus H01, this is the actual one, and you see that that can be written as H2 minus H1 plus half V2 square minus V1 square. This is what we get, and the maximum or ideal steam turbine work we could have got it as H02 minus H01s, and that is again given by H2 minus H1s plus half V2 square minus V1s square. Now we talk about the definitions of efficiencies in turbine. We can talk about efficiencies in terms of the static enthalpy or the stagnation enthalpy. So, if we say that the change in kinetic energy is not significant, we can neglect this change relative to a change in the static enthalpy, and we can say that eta SS is nothing but H2 minus H1 divided by H2 minus H1s. That is, we are talking about only the change in the static enthalpy in the real situation to the maximum or the ideal situation of H2 minus H1s. However, many times or most of the times we would like to express in terms of the stagnation quantities, because the kinetic energy change is also going to be accounted for, and this one is known as eta SS. SS stands for static to static efficiency. And if we talk about that exit kinetic energy is important and is not same as the inlet kinetic energy, the kinetic energy change is significant, then we can talk about whether exit kinetic energy is utilized or not. Let us take two examples. Let us say that we have an aircraft and we are talking about the last stage of the turbines, because many times these turbines, as I will show you, will have multiple stages. That is, it goes from one row of blades to the next row of blades and so on and so forth. Ultimately, we are talking about the last stage of the turbine. So, if it is in the last stage of the turbine, then in an aircraft, then what happens, the gas that comes out also helps in the propulsion. So, that means the kinetic energy of the gas that comes out is utilized, it is desirable to have some kinetic energy. Or else, if we talk about an intermediate stage in a turbine, then that kinetic energy that is left out from the one stage will go to the next stage and is also utilized, it is not wasted, and hence in this case we can say that exit kinetic energy can be utilized for two cases: as an intermediate stage of a multi-stage gas or steam turbine, and in the last stage of a aircraft gas turbine where it contributes to jet propulsive thrust. And in these cases we define an efficiency in terms of eta TT. TT stands for total to total efficiency, and we say it is H02 minus H01 divided by H02 minus H01s. That is because the kinetic energy is useful. But let us say that we are talking about a land based gas turbine and we are talking about the last stage. Ideally, if it is possible for us, then we would not like to have any kinetic energy of the flow living with the flow. We would like to utilize all the kinetic energy, and if we fail, that means some part of the energy is wastage. So, it brings us to the next stage. Next question is that it is not utilized. If the kinetic energy is not utilized, like in a land based gas turbine, where the last stage ideally I would have liked the fluid to leave without any kinetic energy, but that is not possible. That means some energy has not been extracted from the fluid, and that means our efficiency should be differently noted, and this is given as eta Ts, which is H02 minus H01, because that is the actual energy available to the turbine, whereas the ideal world will say that ideally there is no energy coming out of the fluid, and hence ideally the fluid should have come out at H1s, and hence the energy that will be available ideally should have been H02 minus H1s, because the fluid should not have left with any kinetic energy. Whenever the fluid leaves with any kinetic energy, that is a loss from the turbine perspective, and in this case if it is not utilized, we say that we should use eta Ts, or total to static efficiency. Thus, we know that there are different ways of expressing the efficiency of a turbine. And last thing about the compressor, and we can talk about the specific work and the efficiency. You see, in case of a compression, it starts at a lower pressure, lower temperature, and goes to a higher pressure, higher temperature, because the gas is compressed, and 1 is the state in which the fluid enters the compressor, 2 is the state in which the fluid leaves the compressor, 01 and 02s are stagnation states in case of the inlet, and 02s for the idealized case with constant entropy or isentropic compression, idealized world, and real is 02. So, in case of compressor, we say that H02s minus H01 divided, that is H02s minus H01 is actually the amount of energy that should have been used, because that is what goes into the fluid. But what actually we need is H02 minus H01, because we have to overcome the losses. So, in this case we get for the compressor H02s minus H01 divided by H02 minus H01, and this is the end of today. So, let me summarize what we have learned in basic thermodynamics. We talked about thermodynamics, and we found that thermodynamics along with fluid mechanics forms the backbone for understanding turbomachines. In thermodynamic analysis, turbomachine is treated as a black box whose inside details are missing. We talk only about the energy interactions. First law is essentially a statement of the conservation of energy. We applied it for the control volume approach, and energy transfer in turbomachines can be dealt with control volume analysis corresponding to steady state steady flow equations. Second law poses directional constraint and helps in defining a property called entropy. Actually, it leads to the property of entropy. The second law combined with the first law helps us to determine the maximum work obtainable from turbines or the minimum work that is required by compressors and pumps. Various definitions of efficiencies are introduced. These efficiencies and losses for actual machines will be covered in the next week. So, as I was saying that in thermodynamics we have dealt with turbomachines as a black box in which some fluid enters with some energy and leaves at the exit with some other energy, that is a steady state steady flow. So, there is no mass being accumulated, and we have found out the energy conservation equations based on first law. We have also talked about the second law. What we now need to do is understand what happens inside a turbomachine. To get to that, we need to know what is the construction of a turbomachine. So, in the next class we will talk about the different aspects of turbomachines, the classifications, and of course, we will continue with that discussion on the principles. Thank you.